Hello. Now in this session today we will try to understand a very interesting phenomena in the dynamics called as the gyroscopic effect. Now the term gyro included in this effect is for the bodies which are spinning about an axis. Now there are many mechanical systems where there are components or bodies or parts of the mechanisms which are rotating. Now it is seen that as a whole, when this entire mechanical system is rotated about or gets rotated about some other axis, then the behavior is kind of unpredictable. Unpredictable in the sense we maybe as we expect that body to move in a particular direction, but we see that it is not moving in that direction, rather it is moving in some other direction, or it is trying to rotate about some other axis which we have not expected. Now to understand this phenomena, we will go through, or I'll try to explain it with the help of this example. So let us say there is a disk of some mass m, and which is mounted on a shaft, let us say, and this is the shaft axis, right? So this is this is a disk which is having some mass, considerable mass, and it is rotating about this axis. So let us say it is rotating in this fashion, and this shaft is, say, supported. There is a support, so maybe in this fashion there is a support fine. So it is supported this way, so let us say it is supported this way and it is spinning. Now let us try to think two situations and try to predict what will happen. Now if say this is not rotating, or this is stationary, right, and if I remove this support, what will happen? Obviously this, we can very well say this body will fall down, right? Now let us take a second situation where this body is not static, but rather it is rotating with some speed or angular velocity, say omega or speed n. It is rotating, right? Now, and in this situation, if I remove this support, right, again my common sense is saying that it is supposed to fall down, right? Now, but this does not happen in this case when this body is rotating. Fine. So when this body is rotating, and if I remove this support or one of the supports, I see that this body does not fall down, rather this body starts to rotate. Instead of falling down, this body starts to rotate on this horizontal plane. So for that, if we say mention the axis now, so let us say this is one axis, so I denote it as x-axis. From this center, this is, say, the second axis which is perpendicular to the x-axis, so I call this as the y-axis, and this is the third axis, which is so the z-axis. Fine. So the x-axis about which this body is spinning or rotating, this is the y-axis and this is the z-axis, right? Now what I am saying is, or what we are trying to understand here is, the moment I remove this support, I say that what will happen is this body is not going to fall down, rather it will start rotating. That means this shaft, the shaft is the spinning axis. So I'll call this axis, the x-axis, as the spin axis, right? Now the moment I remove this support, so this body, the mass is going to act downwards, so this is supposed to fall down. So when anyway this mass is going to act downwards, so this point will be acting as a pivot for this. So as if a moment or a torque is getting applied, so I'll call this as the applied moment, or say the torque axis, right? So the moment I remove the support, so a moment or a torque is getting applied, due to which it should fall, but it does not fall, rather it starts rotating in the xz plane about the y-axis. Now this may rotate in any of the direction, that we'll see when we do the analysis in exactly which direction it is going to turn. But anyway, this is not going to fall down, rather this is going to rotate about the y-axis. So rotate means the body starts moving, the entire system starts moving about the y-axis. So this is called as, this movement or motion is called as the precession. So this y-axis acts as the precession axis. So this effect is called as the gyroscopic effect. Now this will happen only when this disc is spinning with some considerable speed or angular velocity. So how can we explain, or rather in a way define, what is gyroscopic effect? So in point wise, if we say, so when a body is rotating about an axis, so this body is rotating about the x-axis in our case, and this x-axis is the spin axis. So when a body is rotating about an axis, and second, what is happening, and the axis of spin, that means the x-axis, and the axis of spin is rotated. Now this is getting rotated due to the applied moment or the torque, so whatever may be the condition, but due to some reason, so this starts rotating or have a tendency to rotate, or I can say a torque gets applied on the spin axis so that it rotates about z axis is rotated about a perpendicular axis. In our case, if we see this case, this is it is rotating or having a tendency to rotate about the z axis, right? Then what is happening? The body starts precessing means, or maybe it starts rotating or turning, I'll say turning about an axis. So in our case, it will start rotating about an axis, an axis mutually perpendicular to both the other axis. That means in our case it will be mutually, that means y is mutually perpendicular to x and z. So in our case it is perpendicular to x and z axis. So what is happening? Try to understand the situation. When a body is spinning about an axis and the axis of spin has a tendency or starts rotating about an axis perpendicular to the spin axis. So this z axis is perpendicular to the x axis. Then what happens? The body starts precessing, or instead of falling down, it starts precessing or moving or turning about an axis, which in our case is the y axis, mutually perpendicular to both this axis. So it is perpendicular to z as well as perpendicular to x. So this phenomena or this effect, so this is called as the gyroscopic effect. Fine. So this is how we can understand here, and practically we can see this is happening. Right? Now the question arises, why this might be happening. So let us try to understand how do we get this precession motion. Now what is happening here is due to the subjected condition. What is the subjected condition here? That maybe somehow one of the supports is removed. So the tendency is that the body is falling down due to the applied torque or momentum. So the body starts precessing. So when this is the case, so let us try to understand this. When this, so if a moment is getting applied on the spin axis, then the body starts precessing. So the vice versa also can happen. So if I forcefully try to move the spin axis, then instead of then in that case a moment will get applied in the system, right? So that or moment or a couple will get involved or get applied in the system, and that couple is called as the gyroscopic couple. So now let us try to understand why this might be happening. So let us try to understand then, how do we get this precessional motion? Now we know that now these are all spinning bodies. That means we are dealing with all angular displacement conditions, so angular velocity condition. So anyway, we know that the angular velocity is a vector quantity, right? So when we say it is a vector, then it is having three things. Or so one, it will definitely have magnitude, it will definitely have direction, the vector will have a direction, and third thing, as this is an angular condition, so it will also have a sense of rotation, right? So this vector this vector of angular velocity will be dependent on these three values. So if one of these three values is changed or gets changed, then definitely omega is going to change, right? So that is what we are trying to understand here. So now our task is to, or we are trying to understand why this might be happening. Now, to express the vector angular for angular velocity, the right hand screw rule we will apply, we have to apply, right, for vector. So when the what does the right hand screw rule suggest? So when my fingers, so from my point of view, if I see, when my fingers of the right hand are curled clockwise, then the thumb will be pointed outward. So this will be the direction of the vector. So let us try to understand in this case, in this situation, say if the observer, or if the observer is looking at this system and I am showing that the omega, the sense of rotation to be this, that means with the right hand, if I see, it is turning clockwise for me, it is turning clockwise. So I will curl my fingers clockwise, so I see that the thumb is pointed outwards. So for the angular velocity vector, when I am going to draw for this omega, so from the pole it will be moving outwards from me. So this will be the direction of the vector, and this direction of the vector is getting decided by the sense of rotation. So if the sense changes, if the body is spinning counterclockwise, then in that case I have to turn my fingers counterclockwise, so the thumb will be pointing towards me. So in that case the vector will be pointed in this direction, right? So let us try to understand then how this motion in about the third, or the precession motion, is coming into the picture. So let us consider a body is spinning. So maybe I show it this way, it is turning counterclockwise. So this will be the vector for, so it is turning by angular velocity omega, so the vector will be pointed towards me, right? And at an infinitesimally small time interval, what is happening is the maybe the direction of this vector is getting changed, right? So as we have seen, so maybe this gets changed. So this is omega, so this has changed, omega plus del omega, and this change in the direction is an infinitesimally small change, which is del theta, right? So if I draw the vector diagram for this, so say this is the pole for the vector, so this is omega, so I name this point as A, and this is the omega plus infinitesimally small change in omega, and this is del theta. So this is the change in the angular velocity. So this change in the angular velocity can be understood. So if I resolve this change in the angular velocity. So I name this point as C. So now we can see that the change in the angular velocity at infinitesimally small time interval will have these two components, one which is parallel to omega and the other which is perpendicular to the vector of omega. So this is the tangential component, right, and this is the centripetal component of this change in the angular velocity. So the rate of change will be the angular acceleration. So if I try to understand the acceleration, because accelerations are going to determine the motion and we are trying to understand the precessional motion, that is, so now I can say this tangential component to be as the AC. So this is the angular tangential component of the angular acceleration, which will be this AC by del t. So what is AC? It will be, so this is pole O. I can say that this is OC minus OA by del t. Now what is OC? OC, I can say OC is omega plus del omega cos of del theta minus AC, OC minus OA is omega, right, by del t. So for in the limit, if I say in the limit when del t is tending towards 0, so del theta for a very small value of theta, del theta cos theta will be 1. So in that case I get this as omega plus del omega. So I have applied the limit, so it will be omega plus d omega minus omega by dt. So I get the tangential component of the acceleration to be absolutely as d omega by dt, which is the absolute change in the rate of change of the angular velocity. This will be the tangential component. But let us see what will happen for the centripetal component of acceleration. Centripetal component will be this is A, I name this as B. So it will be BC. So this is BC upon del t. And what is BC? This is equal to omega plus del omega sine del theta by del t. So again in the limit for infinitesimally small infinitesimal del theta condition, so sine theta will be del theta. So for del theta to be infinitesimal, if I say, so I get centripetal component of acceleration, this to be omega plus del omega plus into d theta by dt. So it will be omega plus, now sorry, so this becomes omega d theta plus d omega by d omega d theta by dt. So product of smaller value will be further a more smaller value. So I get this as omega dt d theta by dt. So d theta by dt, if you see, so this displacement which is in this plane, so this is the movement, so this is called as, so d theta by dt, this is the, so this is the spinning velocity, spin velocity, angular velocity, and this is the precession velocity. So you can see, so by this we can understand as if the angular velocity changes, then of course there will be angular acceleration, and we get in angular acceleration, we see that the centripetal component is product of the spin velocity and the precession velocity. So if at all somewhere, whatever way or whatever condition, if there is change in this angular velocity, then the body will have a tendency, or it will move in the about the third mutually perpendicular axis, which is precessional. So now we will try to determine what is the gyroscopic couple. Now, as I have discussed just now, so if there is a body which is, say, spinning about an axis which is spin, and say due to some reason we have seen that the spinning axis is applied by some torque, then this body starts precessing. So this is precession and this is the applied torque. Now this condition, when a torque is getting applied on the spin axis and the body starts precessing, this condition is called as natural precession. Right? So a simple example can be this, that there is a disc which is supported by two bearings, and one of the bearings is, say, breaks or falls down or gets removed, then an applied torque is getting applied, so the body starts precessing. Second case is if forcefully or by the subjected conditions, this spin axis starts moving about an axis, then in that case a couple or a moment or a torque will get applied in this system, and that couple is called as the gyroscopic couple. So that condition will be called as the forced precession condition. So one is the natural precession condition and the other is the forced precession condition. So how do we separate these two situations? We have to understand, if in the system a couple or a torque is getting or a moment is getting applied, then the body will start precessing about the third mutually perpendicular axis. This is natural precession. Now if deliberately I precess a body about an axis, then the reverse will happen. Then a couple will get applied to the system or produced in the system. That will be the forced precession condition, and that couple will be called as the gyroscopic couple. So in that case, so now if we try to find out the magnitude of this couple, so we'll try to find out the magnitude of this couple. Again so this is a disc which is spinning about this axis. So we see this, we consider the three mutually perpendicular axes. Fine. So this is the spin axis, this is the precession axis. So in that case this will be called as the gyroscopic, so gyrocouple axis. So this is the gyrocouple axis. So we consider the x-axis to be the spin axis, y-axis as the precession axis, and z-axis as the gyrocouple axis, right? Now, to determine this magnitude, now we say that moment is getting applied. Now, according to Newton's law, it says what? Every body will tend to be in its state of rest or of uniform motion. Uniform motion means one directional motion until and unless it is acted upon by an external unbalanced force. So when the body is moving in a straight path, it will continue to move in a straight path until and unless an external unbalanced force is applied. Now the reverse may happen. So by this application, it will if it is moving in its own direction. Now if I change the direction, then the reverse will happen. So in that case, a force will get involved in the system, and this will be equal to the rate of change of momentum. So same thing gets applied for this angular condition. So if this is rotating, so this body is rotating by angular velocity omega, so angular momentum, so this is having some mass, so I consider here as this is a spinning body or a rotating body, so I consider the mass moment of inertia. So what will be the angular momentum? It will be I omega. So the vector of this angular momentum will depend on the vector of the omega, right? So say if this body is turning in clockwise sense, so again I apply if I am the observer, so I am looking at it in this direction, so according to me it is turning clockwise, so I apply right hand thumb rule. So when I apply right hand thumb rule, so the vector for angular momentum will be this. So I name this point as, say, let us say A. So this is the pole, I name it as O. So OA is the vector of angular momentum of the spinning body, which will be equal to I omega, right? So now if the direction of the spin axis changes, just now we had a discussion, so the velocity is depending on the magnitude, the direction, and the sense of rotation. So out of these three, if any one changes, then omega is going to change. Now if omega is going to change, then the angular momentum is going to change, right? So say if it changes, so there is this change because the direction of the vector is getting changed, because this vector will be perpendicular to the plane of rotation. So let us say this is the spinning body and this is the axis. So if the axis is getting changed, that means the plane of rotation is getting changed. So the direction of vector which is perpendicular to the plane of rotation, that is going to change. So there will be change in the angular momentum, and say the change in angular momentum, though, see what is happening here is, though the magnitude of omega is not changing, but the direction of the vector is changing. That means, so still, so let us say this point is B, right? So I can say that this arc AB is the change in the angular momentum for a very infinitesimally small condition, I say, which is happening at a very infinitesimally small time interval. So in that case, this couple, so whatever this couple which is gyroscopic couple, I denote it by CG, this will be equal to rate of change of angular momentum, right? So this is equal to the arc AB, right, which we are saying infinitesimally small change in I omega. I omega is the angular momentum. So what is this AB? AB is this arc. This is a small angle. So this arc length, I can say this is equal to r theta. What is r? I can say this AB is OA del theta by del t, right? Rate of change of angular. So this is change in the angular momentum. So arc AB is equal to r theta. So r is OA del theta. So this will be the gyroscopic magnitude of gyroscopic couple. And what is OA? OA is I omega del I omega, which is, what is I omega? I omega is the angular momentum of the spinning body, right? I omega is the angular momentum of spinning body. So this is del theta by del t. So again, in limit, I say for infinitesimal theta condition, I can say that gyroscopic magnitude of gyroscopic couple is equal to I omega d theta by dt. And what is d theta by dt? It is the precession. So this is moved about the precession. So gyroscope magnitude of gyroscopic couple is equal to I omega into omega p. So I get the magnitude of gyroscopic couple. So when I want to determine, if I know what is the precession velocity, so for example, say these two are the wheels of a vehicle which are spinning about this axis, right? And it takes a right turn, let us say. So when it is taking a turn, the wheel axis is forced precession condition, right? So that means a couple will get induced in the system. So a couple is getting applied in the system, which is gyroscopic couple. So in that case, so if say this is the axis of rotation of the wheel and it is taking a turn, so about this axis a couple will be experienced. So it will be adding an extra load on the bearing, which we might not consider while designing the bearing situations, right? So in this, so maybe we have designed the bearings only in the plane conditions for just a straight motion of the vehicle, but things are changing if when the vehicle is taking a turn. So when the vehicle is taking a turn, the dynamic situations will change and the gyroscopic effect will come into the picture. And from the expression we can see that the magnitude of this couple is definitely very much dependent on the angular velocity of the spinning body, right? So if this is very high, if a vehicle is moving at a very high speed, then this couple value will be very high. So couple is two forces acting separately. That means the load on the bearings will increase. So what is gyroscopic couple? We can see here is that gyroscopic couple is product of the angular momentum of the spin body. And what is this? This is the precession magnitude of the precession velocity, right? So the magnitude of the gyroscopic couple is product of the angular momentum. Now this angular momentum will be high if the angular velocity of spin is very high, and precession velocity if it is, if for example, if a vehicle, if I am talking about, it is taking a turn at a very high speed, then the precession velocity also will be very high. So maybe in that condition the magnitude of the couple will be very high. So the forces acting due to this couple, that those magnitudes will be very high. So that is how then in the given situations we can determine the magnitude of the gyroscopic couple and take proper decisions while designing a system for dynamic condition. So what we have seen in this session is, we have understood what is gyroscopic effect, how the precessional motion is coming into the picture, and we have as well seen what can be the magnitude of the gyroscopic couple. So in the coming sessions then we will see these application of this situation. We will try to understand the situations where these are coming, like the conditions for four-wheeler, then floating vessels like ships and boats, aeroplanes, two-wheelers, how the gyroscopic effect affects a given mechanical system. So that's all for this session.